Hello and welcome to the presentation of our project titled Assessment of the Parallel Performances of PermaFoam up to the tens of thousands of cores and new architectures. I'm Doğukan Teber and I'm here with my partner Stavros Dimou. We have spent the summer in association with the Geosciences Environment Toulouse, or in short GET, supervised by Thibault Xavier. Our project consists of two parts. The first one is developing a pre-processing utility on OpenFOAM that decomposes a mesh for parallel execution faster than Decompose bar, and the second one is performance analysis of PermaFoam in an MPI environment. GET Laboratory is coordinating a project called Hyperborea, and our project acts as a stepping stone. The aim of Hyperborea is to quantify the effect of global warming on permafrost areas based on numerical studies at the watershed scale. Permafrost is a thick subsurface layer of soil that remains below freezing point throughout the year, occurring chiefly in polar regions. Unfortunately, due to climate change, these permafrosts are melting and causing severe impacts on our lives. For instance, many northern villages are built on permafrost. When permafrost is frozen, it's harder than concrete. However, thawing process can destroy houses, roads, and other infrastructure. Permafrost melting also causes of releasing greenhouse gases like carbon dioxide and methane into the atmosphere. In addition to that, when permafrost thaws, so do ancient bacteria and viruses in the ice and soil. These newly unfrozen microbes could make humans and animals very sick. To help predict the impact of permafrost thaw, we will use OpenFOAM and PermaFoam. OpenFOAM is a free and open-source CFD toolbox used in academia and industry to solve a wide variety of computational problems. And PermaFoam is a hydrology solver which is built under the OpenFOAM framework. The life cycle of a typical OpenFOAM problem contains three parts: pre-processing, solving, and post-processing. Pre-processing involves creating and organizing the mesh. Solving, as the name suggests, involves solving and managing OpenFOAM cases. And post-processing involves visualizing and examining the result. For Hyperborea project, we need to run PermaFoam solver on parallel. Because of that, the mesh needs to be decomposed for parallel processing. However, the current pre-processing tool, Decompose bar, is taking too much time to finish its execution. For instance, it takes approximately a week to decompose a mesh that has 1 billion cells on 7,056 processes. To speed up this process, we have built a new parallel tool, parallelDecompose. ParallelDecompose decomposes a mesh and fields for a parallel execution faster than Decompose bar. Without diving into the technical aspect of the code, I would like to give the results we obtained this summer. If you'd like to learn more about the technical parts of parallelDecompose, you can visit the code repository on GitHub or you can directly contact me. So when we run Decompose bar on a mesh case that has 850,000 cells, it took 1 minute and 8 seconds. When we run parallelDecompose for the same mesh case on 324 processes, it took 32 seconds. We have been able to reduce the computation time by approximately 50%. This is the first version of parallelDecompose. There is a memory problem due to MPI's distributed memory architecture. This problem could not be solved in this version due to lack of time and the complexity of the OpenFOAM codebase. It is expected to be solved in the next version. Now I will pass over Stavros for the other part of the project.
Hello from me as well. I'm Stavros, and today I will present you the performance analysis conducted on PermaFoam. The supercomputing infrastructure alone was used in order to test the PermaFoam behavior while making good use of multiple cores. The performance analysis was conducted for both the Dimou case and the Dimou case sinusoidal climate forcing test cases provided by the hydrology repository. The study was split into three parts: the execution time analysis, the linear solver analysis, and the code profiling. Concerning the execution time analysis, the tests were conducted while using 1, 36, and 72 cores, corresponding to a serial version of PermaFoam, and utilization of 1 and 2 nodes of PermaFoam. The execution time when using 36 cores compared to 1 is much smaller, and specifically, the completion of all operations around 2.5 times faster with 36 cores. The run with the 72 cores, however, was not efficient, as the mesh dimensions used was quickly multiplied by 80, and as a result, the domain was over-decomposed quite quickly. Also, concerning the time spent on each equation for different number of processes, the heat transfer equation is the most time-consuming on all cases, with Pilz's equation being 122% faster with 36 cores. The linear solver of permaFoam contains a few iterative operations, and the purpose of this analysis was to observe how those iterative operations evolve depending on the number of cores. The results show that the total iterative operations are the same independent of the number of cores. However, we have high frequency of bigger number of iterations and low frequency of small number of iterations as the number of cores increases. On the other hand, for a small number of cores, the opposite happens. It is critical to mention that for the value of 0 iterations, the frequency stays consistent and the same, independent of the number of cores used. For the last part of the analysis, we profiled the code using VTune and LWP Bool MPI lightweight profiler. While using 2 cores, the total MPI environment utilization time was 30% less than that of the 36 cores, and the time caused by the MPI component overfit was 3.01 times less as well. Regarding the most time-consuming functions, MPI reduce spends around 3.6 seconds of total work, while MPI receive spent 1.3 seconds respectively, as both dedicate a lot of time for communication with other processes. All the other functions had a very small execution time. Regarding the future work, the project can be expanded by finding a memory-efficient way to decompose a mesh in parallelDecompose, to conduct an analysis of permaFoam with more cores and on other high-performance computing infrastructures, and to make use of different test cases with bigger meshes to avoid over-decomposition effects. Thank you for your attention. All questions are welcome.